Okay, awesome. Also, okay, there's a question. How old are you? Just curious. I'm 20 years old. I'm turning 21 next week, actually. So yeah. Um, I live in Orlando, Florida. Yeah. Also, if you guys have questions, feel free to interrupt because I won't really be monitoring the chat. It's kind of hard to see the chat while I'm like on share screen mode. But yeah, okay, cool. Back to the first problem. Yeah, so we're given an alphabet, and then we're also given an ordering of what Farmer John hears, or yeah, Farmer John hears. And so basically, what they want us to know is on any given iteration of the alphabet, Farmer John will hear some characters, and they want us to answer how many times, what is the minimum number of times that Bessie must have gone through the alphabet for Farmer John to hear what he has heard, right? So were there any kind of questions about this problem? Did everyone understand what they were asking at the end of the day? Okay, cool. So if the problem makes sense, okay, chat. Yes, okay, everyone understood. Great.
Just because of screen sharing, you might want to like zoom in a bit. So it's.
Oh yeah, is it zoomed out? Is it hard to see? Is this better?
Yeah, that's better.
Okay, cool.
It was fine before, but I was saying it'd be easier.
Okay, sure. Cool. So yeah. So let's kind of think about our thought process, or I guess maybe you guys can hop in for those people who didn't solve this problem, or also if you did solve this problem, what were some initial thoughts when you first read this problem of how to attack it?
Convert everything into numbers.
Okay, and why would you want to convert everything into numbers? How does it help?
Well, you can't really compare the positions of like alphabet. So if you use numbers, I guess you can use like greater than and less than.
Okay. And so I guess why are you comparing numbers or why are you comparing these letters together? Which letters are you thinking of comparing, and why do you need to compare them?
Yeah, so I just went through the string, the alphabet, and then the first letter in the word that we need to make is M, and then like if the next letter in the word is after that, then we can include it in the same alphabet, but otherwise you have to start a new alphabet. So I kind of like had to compare letters there.
Gotcha. Yeah, so that's definitely true. So that's kind of a good observation you made, where basically, if you compare adjacent letters in your actual string, right? In order for the second letter to show up in the same iteration as the first letter, right? The second letter must come after the first letter in the alphabet, right? Does that make sense to everyone? Why that's true? Yep. Okay, cool. So that's definitely a good observation, and that's kind of we can quickly realize that that's kind of the only way we can save iterations, right? In the worst case, we just go through the alphabet once for every letter, but sometimes we can save letters like this. So I think that was Advite who said that. So yeah, we can definitely use this idea. So it turns out that you don't actually have to create this extra work for yourself and convert the letters to numbers, because there are ways that we can compare string characters, and so we'll take a look at that when we implement it. So one thing that I like to tell students, and you want to get in the habit of this eventually. It's very hard once you start out, but you want to try to go into a planning phase before you start coding. And then once you start coding, you shouldn't be thinking necessarily like about the solution of the problem, right? You kind of want to separate these two problem solving stages, because usually when you get to coding, you're focused on not writing bugs, really just trying to get the logic out. And so you want to have all these thoughts kind of pre-formulated. So what I'm thinking in my mind now is, all right, what I can do is I'll go through every single letter in my string, right? This being the string. And for each letter, I'll go through the alphabet. And once I find my letter in the alphabet, I'll move my current pointer, my current position in the string, one over. So that might have been a bit unclear. So let me just pull this up and we can see what I mean by that. So we have like our alphabet A, B. Let me actually use my mouse. A, B. Oh God. 1 second. A, B, C, D, etc. And then our string was like mood, whatever. Okay. Sorry for the bad handwriting. But essentially what we can maintain is we can maintain a position in our bottom string, right? So we're gonna start at the beginning, and we can also maintain a position in our top string, right? And what I'll do is while I have not found the character at the bottom position in my top string, I'll keep incrementing this blue pointer, right? So I start here, A is not B, so I'll move it over here. B is not, oh, sorry, A is not M, B is not M, C is not M, so on and so forth until I hit M, right? So then my blue pointer will be at the letter M, way down here in the alphabet. And now that I've found my letter, I can move my red pointer to the next letter, right? Just like that. And so now that I'm on this, then I can continue with my blue pointer, right? And so my blue pointer will now go L, M, N. N is the next one, O, and then we see O, and then it's like, oh, here's O again. Let's now move this guy over, right? So this technique that we're describing, it's very straightforward, kind of the algorithm, right? But I guess the technical term for this technique is called a two-pointer sweep, where you're kind of you maintain 2 pointers and you're just sweeping through in one direction of the data. In this case, we're going to then restart at the alphabet. Once we get to the end of the alphabet, we can restart and go again. Okay, so that's kind of the high level overview. Let's now go ahead and code this. Could you use unsigned char? Yeah, so you can do that. I guess do you code in C++, Advait? No?
Yeah, I do.
Okay, yeah, for sure. So I'll just be coding in Java today. I don't know what language people use. Let's see. Yeah, do most people who code in C++ or Java? Yeah, do people want to share their language preferences or what they used in this past contest? And guys, for the people who didn't come, please feel free to unmute yourself. This can just be a very just casual conversation because it's also hard for me to open the chat like this. Jason uses Python. Pranav uses Java. Okay, yeah, good mix.
I use Python, but I am learning Java and know Java, so
Awesome,
I'm good
awesome.
if you do the solutions in Java.
Cool. Good stuff. Yeah, so in general, Python's okay to start, but you want to generally move to a more performant language like Java or C++, because we'll talk about this at the end of the problem, but there's this notion of like complexity or how long can you estimate your program will take, and your programs can run at different speeds in different languages, which is, you know, good and bad, but Python is generally slower than Java and C++, so it kind of sometimes you can get hindered in competitive programming. But yeah, so let's just go ahead and yeah. What was the question?
Okay. No, I was just wondering what language you code in.
So I code in C++ normally for competitive programming, or Java, depending on the problem. Sometimes if it's a particularly hairy implementation problem, there's nicer things in Java that can be useful. But yeah, it really doesn't matter. But the majority of people use C++ though.
I mean, like I use Java, except like usually most people that I do USACO with, they use C++. So like,
Right.
I guess like I will talk to you about this after because I need to decide this because I'm not sure if I should completely move to C++ or stay in Java.
Sure, we can talk about that a bit later. But let's go ahead and get started with the implementation. So scanner is just one way you can read an input. One thing to note is scanner is slow compared to other ways of reading an input in Java. And so if you have a problem with a very large input, and this is outside of the scope of bronze, just to be clear, but if you have a problem with a lot of input, you want to use something called buffered reader. And maybe in another problem, I'll use buffered reader to show you how to do that. But yeah, so let's just go ahead and read in the alphabet. Okay, and then we'll read in our string as well. Okay, what are these questions? And please, if you feel comfortable, just go ahead and yeah, okay, I can explain buffer reader later. Yeah. Okay, cool. So let's go ahead and implement this pointer technique. So I guess when I first learned like this idea of a sweep and pointer, I was like, how do you actually implement this? Like, what does a pointer mean? Does anyone have any ideas of an easy way that we can represent our position?
I mean, you can, so are we taking, well, you would just take a specific index of your original string, which you called alpha.
Right. So we can just keep a current position or just use an integer to represent our index.
Or you could just like point to the storage address.
Yep, you can also do that. I guess to actually then use pointers is a bit. You can do it. In my opinion, it's overcomplicating. I think it's simpler just to use an index. But yeah, you can definitely do that. So now we're going to keep running our algorithm, right, until we get to the end of our string s, right? So to do this, we're going to use a while loop since we want to do like while our current pointer isn't to the end, right? So literally while cur is less than s dot length, we need to continue our algorithm, right? Okay, so now what do we do at each stage of our algorithm? Well, like in our picture, we were moving the blue pointer over, right? So basically what we need to do is we need to find the current letter in the alphabet. So to do this, we can just use a for loop. Oh God, let me just type it. So we can just use a for loop. Cool. And so we want to look for our current character. So does anyone know how to like compare characters or an easy way to do this?
Yeah, I'm like, sorry, but can you zoom in clips again?
Oh, yeah. Sorry about that. Is this better?
Yeah, I was just saying.
Okay, cool.
Because my zoom window on my computer is a bit small, so.
I see. Okay, yeah, maybe this is a good size. Okay, so we're gonna we can use the car@at function, and so that'll grab the letter at the current index we provide. So we want to compare our current position of s, right? And we want to see if that's equal to the current position of alpha, right? Does everyone understand what this line is doing? Right, we're just checking to see if the current position in alpha in our alphabet is in fact our current character, right? And if it is, what do we want to do? If it is, then that means that we want to move our position in our current string, right? And we want to increment that because we've found this character, so we can move on to the next character, right? Okay, so I guess what do we also need to be keeping track of? We need to be keeping track of what our actual answer is, right? Like how many times do we actually get through the entire alphabet? And we can store that in a variable called res for results. Right, and so basically every time we go through this, this for loop, that's going through the alphabet once, so we can increment res. Okay, so this logic looks pretty good, but we're still missing one thing. Does anyone kind of know what we might be missing as well? Does anyone see a bug that we could have introduced here?
I have a quick question.
Yeah.
So, current is just where we currently are at in ABCD in the alphabet, right?
No. So cur is where we are in our string. Yeah, let me make that clear. So cur current index in string s. Right. So the way you can tell that is because we're indexing into s here with cur.
Okay, and then s is, for example, mood.
S is mood, exactly. S is mood.
Okay. Yeah, and then res is
going to be our actual answer. That's counting the number of times we go through alphabet.
Okay, cool. Thanks.
Okay,
Wait.
so does anyone see where we might have a bug here in this code?
What happens when like the blue pointer gets to the end of the alphabet?
Yeah, so what is the blue pointer in this code? What variable it represents the blue pointer?
Alpha, I think.
So alpha is the string itself. Alpha is the alphabet itself. It's not the blue pointer. Let me check chat. What's happening here?
I think the blue pointer is just the I variable that's going up and down.
Exactly right. So I is the blue pointer. So since we've implemented the blue pointer with a for loop, it automatically will check if it's the end of the alphabet, and then it'll just end. The for loop will end. right? Does that make sense how the blue pointer is handled in the for loop? Are people familiar with how for loops work?
Yeah, I got that.
Okay, cool. So does anyone kind of see what a bug might be? And we can just try running this. Maybe this works. All right, why don't we just try running this on the sample? So we get a string out of bounds. Right, so how do we debug this? So it's telling us that we're getting string out of bounds here. So there's two places in this line where we might be out of bounds, right? What are those places? Either here at I, right, or here at cur. One of these two things is out of bounds. Which one of them is out of bounds? Because we know for a fact one of them won't be out of bounds.
Cur is out of bounds, right?
Cur is out of bounds. And the reason why I is in bounds is because I is controlled by this for loop. So we know it's 100% in bounds. Does anyone know why cur might be getting out of bounds? Where is our check to make sure cur stays in bounds? Can you paste the input into chat?
Cur stays in bounds. We can, like, what do you mean? Do you just want to like keep checking which like number cur is?
Well, so I'm just asking in general, like why is cur getting out of bounds, right? Or like where do we normally check? Like, okay, so the check to make sure I stays in bounds is in this for loop condition right here, right? Where is the equivalent check for cur that is making sure cur is staying in bounds of the string s? Cur is getting bigger than the length in the for loop. That's right, Jason, exactly. So the check to make sure that cur doesn't get out of bounds is in this while loop right here, right? Cur is less than s.length. That is the check to make sure that we only want to keep going with cur while it's less than s. But like Jason pointed out, we're incrementing cur inside of the for loop. So what can happen is if this condition keeps on matching, then cur might keep getting incremented on the next iteration of the for loop. So we can print this out to see what's happening. So we can print out cur here. Right, so yeah, so okay, the output is a bit hard to explain. Let me see how to explain this. So we can just actually walk through this really quickly in this example, right? So what happens, we start at m, we go through the for loop, we keep checking until we hit m. Once we hit m, cur gets incremented to 1, right? But this for loop doesn't end, right? The for loop continues, right? So then we move on to n, and then we move on to o, where we see it matches again. Cur is now 2. Or sorry, cur is yeah, sorry, cur is 2. Cur is 2, my bad. Or it's 0 indexed. So cur would be cur starts at 0, it got incremented to 1. Now it is 2. What am I saying? Yeah, I was correct. Okay, so cur is now 2. So that means it's on the second O, right? But this for loop increments to the next letter, which is P. And so it'll continue going through the end of the alphabet. And it won't find any more matches, right? So then it goes back to the beginning. It goes all the way to O. It finds that it's O. So we're back in this if statement. And cur is now D, right? Cur is now 3. So that's the last string, last character in mood. So that's D. So then it goes through the for loop again until it finds D. Okay, so now we're in the position where cur is on D and I is also on D in the alphabet. And it goes into this if statement, right? So what happens to cur? Cur was 3. And what happens now? We increment cur and cur is now 4. So cur is now 4. So what happens on the very next iteration of the for loop? I is now E, right? I now points to E, and we do this check. So we're checking alpha.char E, or whatever the 0, 1, 2, 3, 4. Alpha.char 4 is equal to s.char 0, 1, 2, 3, 4.
Wait, if you put a break statement, does that fix it?
Yeah, so what would a break statement do? So where would you want to put the break statement?
just after cur increments.
So if we put a break statement here, then go back to this, and I'll get you 1 second, Pranav. If you put a break statement here, think about what happens in the first case when we're going through the M and then the O. So we'll match on the M, then we'll do cur plus plus, but we'll do break. And break breaks out of the for loop. So that means that this O isn't going to be found on the first iteration. It'll be found on the next iteration.
Oh, okay.
Right. So putting a break here will give us the length of the string every time. Right. So this will give us 4. Right.
Yes, like is the problem because like you don't have an index 4 in mood?
Right. That's the problem. So what's one easy way that we can fix this? So basically, we just want to add this condition after this if statement as well, right? Or you can just do this at the beginning of the for loop if you want to, right? Where if cur is equal to s dot length, so that means that we're done, right? We've gone through the entire string. Well, now you can break, right? So Advite was on the right track, or whoever recommended the break was on the right track. But we only want to break once we've gone through the entire string. Does that make sense? There's no questions about this? I find that doubtful. This all makes perfect glowing sense.
Seems good to me.
Okay. All right. So let's submit it then. Let's see if this is right.
No. Like this is not the final code. Like this won't work.
This won't work. Okay. And why won't it work?
Because
Any
like,
ideas before we submit why it won't work?
because we're not taking into consideration the okay, so basically I'm pretty sure this code is gonna print out 4. Let me
Yeah, so we can run it. Oops, that's not right.
oh wait, it's printing out 3. Okay.
So why won't it work? Let's think about why, Pranav, you think it won't work, or what's confusing?
The reason I'm saying it won't work, okay, I mean, I tried it out, it's printing out 3, so it may work, but initially I thought it won't work because I did this question, like in the actual test, and I implemented it differently, and I had like a few more steps that I thought that I added that this code was missing. That's why I didn't think it worked, and like those steps were, for example, I had a variable called cur index and prev index, which is basically current index and previous index. And basically I had mostly the same thing, but I had another part that that checked, that was like if the ith index was equal to a jth. And I can't really explain.
I'm understanding what you're saying. Let's take this offline at the end, just so that we're not talking about your specific solution while there's other people. But I'll definitely help you with that. We can take a look at the end. But let's go ahead and try to submit this and see what happens. So let me log in really quickly. I forgot I have to do this. Okay. 1 second. Oh God, that's not the right thing. Okay, so this was problem A. Oh, let me share my screen again. Sorry. Okay, so let's submit this. Grading in progress. I hope this is right. That'll be a bit embarrassing. All right, so that was it. That worked. So cool. Any questions? Any final questions? I do also want to move it along because we did take a bit of time on that first one. And we have 2 more. But any questions? Glaring questions about that? Okay, cool. Let's talk about the second problem. Why did I stop my screen? I don't know. You still have to look at the problem. Okay, so this problem, let's see, which one was it? Yes, this was the even odd one. So basically the idea here was we have n cows. They each have an ID, right? So there's just a number. And the idea here is we want to group these cows in such a way that the sum of all the IDs in each group has even, odd, alternating this way, their total sum, right? Okay, does everyone remember this problem? Everyone understands what they're asking?
Yeah.
Okay, cool. So yeah, what were some of you guys' first ideas when you tried this problem? And if you solve the problem, try not to give the entire idea away.
Well, the numbers don't actually matter. I just like turned everything into ones and zeros. Just taking the parity basically.
Yeah, definitely. That's a great observation because the only condition we have is that the sum of each group needs to be even or odd, and so yeah, the actual values don't matter, just the evenness or the oddness matters. So that's always a nice reduction you can make when having problems talking about evenness and oddness. Ramsey, were you going to say something as well?
Yeah, I was not able to solve this problem, but I think what I was trying to look at was like, in general, how many even numbers and odd numbers do you need to construct groups that like alternate? And I was able to find that you can actually like make groups like this for most groups of numbers, whether they're even or odd. So it didn't really help me narrow it down a lot.
Yeah. So definitely thinking about that is a very good idea, right? So we want to basically know when are groups of numbers even and when are they odd. So we have some really basic rules about evenness and oddness that we can remember, or if we didn't know this before, I don't think they're very hard to discover either. So when you have two odd numbers, what happens when you add them? What's the resulting number?
Even.
So
Yeah.
two odds are even and odd is odd, and
Mhm.
two evens is even.
Yeah, exactly. Okay, so that's something good to keep in mind. Oops. And then what else do we know about this problem? So what do we know about the total number of even groups or the total number of odd groups we're going to want at the end of this? So like, what is the relationship between the number of even groups and the number of odd groups at the end of some grouping? This must always be true for some grouping. There's two cases.
They're equal or like they differ by one, I think.
Yeah, exactly. And they differ by one in a very particular way. So I think in the problem, they specifically said the first group must be even. So we can have groups that are either like even, odd, right? So we can have groups that either start or end with even and odd, or we can have groups that are like even, odd.
So like even will always be equal to the number of odds or more, right?
Right. And it'll only be more by exactly one, right? That's the key thing here. Right. Does everyone agree with these observations so far? Right. So number of evens can either be equal to the number of odds, or the number of evens can be equal to 1 plus the number of odds. Either of these must be true. Okay. So now maybe with these ideas, we start to kind of have this like greedy mindset. And a greedy algorithm is basically where we always do something. Like there's a very simple choice that we make, and we'll always take this choice. Right. So does anyone kind of see any greedy observations we can make about like how to construct these groups?
Well, I kept track of number of evens and number of odds. So whenever I had to pick an even number, I just like took an even number if there was one, but if there wasn't, then I just like took two odds basically. But first trying to take an even number, and the same thing for odds. For odds, you have to take like just an odd or an even and an odd. Wait, no, but there's no reason to take an even or odd. No, sorry. So you either take an odd or you take three odds. Those are like the cases I had.
Yeah. Okay. So yeah, I think this is a good observation. So basically, what we can notice is that odd numbers are like kind of the easier one to handle, right? Because to get an odd number group, like you need an odd number. Whereas to get even numbers, you don't even need an even number to get even numbers, right? So basically what we want to do is we want to increase the number of evens. So let me maybe say it like this. You can imagine we have like these be like a stack, right? So like we have a stack of like some number of even numbers, and we have some number of odd numbers, right? And so obviously there can be more or less of either of them. But essentially, based on these rules, we have some transformations, right? And I mean, the main transformation here is that we can take like two odd numbers, right? Imagine these two things are two odd numbers. And we can chop them off and add one even number, right? And so remember, one of these cases must be true in order for us to have like satisfy the group's property. So essentially, what does our goal boil down to? Well, it boils down to we want to increase these piles, but we essentially want them to be as close to each other as possible. In fact, they must be like one apart from each other as possible. So we want to basically, if we have extra odds, we want to turn them into evens, right? And then to like level these stacks as much as possible. But what about the other case if we have a ton more evens than we have odds, right? What do we kind of do here? Because right now, the way it's looking, it's not looking like we can make it to this equation. Or can
Well, I mean, to get an even, you can say 10 evens is one even. So you can like replace an arbitrary number of evens with just one even.
Right, exactly. So actually solving this case is easier because we can just squish down a bunch of evens into one even number to satisfy this requirement. So yeah, essentially all we have to do is we just need to transform all of the odds into evens if there are more odds than evens. And if there's not, then we can just take this as the answer.
So like
Right.
also if we have the stack of like if it's really big, then if we're trying to find the maximum, then we only want to take like one even. Like we want to take as little evens, right? From the big stack.
So if we want as many numbers as possible, sorry, I actually circled the wrong thing. So in this bottom case, we're gonna want to do this, right? This case corresponds to this case. So if we have a ton of evens, we wanna end with an even, right?
Okay.
Because we basically want this to be as long as possible, right? So as long as we can put O's here, like let's say we have an infinite amount of evens, right? As long as we can put O's here, we want to use up all of our O's, and then we want to put the last guys in even, and then that'll be our maximum. Right? Does that make sense?
Yeah.
Okay, cool. Are there any questions about like this idea that we have here?
No questions, but I like overcomplicated this problem so much. I had like some 100-line simulation code for this.
Yeah. So let's take a look at how we can maybe implement this. So let me pull this up again. Okay, and I promised a buffered reader, so I guess we'll do that now. Buffered reader in equals new buffered reader. What is this? New input stream reader, I think. System.in. Right. Okay, so this is how you initialize a buffered reader. And one thing to keep in mind when using buffer reader is there's no parsing. So there's no like in.next int. There's no next line. You can only read line by line. And that's what makes it so fast. So in this input, the first line is a number n. And so we can do that by, I'm going to write out this line and we'll see what it's doing in a second. Okay, so what is this line doing? So, what? Oh yeah, so you also have to throw this declaration. You don't have to worry about that. You can automatically import that. So what is this doing? So in.readLine will read the entire first line. So in our input format, the entire first line is the number n, right? Then the next thing, this thing on the left, integer.parseInt, converts the string to an int, right? So remember I said in.readLine will always read in strings. So this is how you convert a string to an int, right? Any questions about what this line does? Does this make sense, how we read in n? Okay, cool. So now the next thing is we need to read in our actual data. And so once again, we can just do this in one line because buffer reader reads line by line. So, but remember it's as a string. So yeah, go ahead.
I'm getting an error in my buffer reader, even though like I imported everything.
Did you add these throws declarations?
Yeah.
What's the error saying?
My IO exception is cannot be resolved to type.
It's saying that you imported IO exception as well, Java.io.
I just imported java.util.star.
So notice this is IO, not util. So you need to import java.io.star as well.
Okay.
Does that make sense?
Yeah. So both of them. So java.util.star does not import everything.
Well, yeah, because think about the path, right? Java.util.star imports everything from util, but this is using things from IO, right? This is like you imported import java.util.star, but you also want to import java.io.star. Is it clear like how these are different?
Yeah, IO is probably like input output.
Right, exactly.
Okay.
Okay, so now we're going to read in the actual array. And so bear with me 1 second. This is going to look a little weird. Okay, but what have I done here? So remember what I said, in.readLine reads in the entire string. So sitting in in.readLine right now would be 1, 3, 5, 7, 9, 11, 13, right? So then I call this dot split function. And what it does is exactly what you think it might do. It does. It looks for spaces in the string, and it'll create new strings at each of these spaces. And it stores that in an array. So now in each index of this data array, I have each number in string form. So what will data.to print if I run it on this sample?
5.
Probably. Let me. Yeah, exactly 5. Cool. So yeah, so going back to our solution now, we're going to maintain the number of even numbers and the number of odd numbers in our input. So what we need to now do is iterate through this for loop again. And we need to just check if each number is even or odd. So remember, one thing we have to do is convert each number because it's in string form, right? Data of I is a string. So we're going to convert that. And this is why like I prefer to use scanner unless the input actually is large, because as you can see, buffer reader is unnecessarily a bit painful. So this is converting each index, right? So if I print out cur and I print out data of I, it'll be the same thing. It's just a different data type, right? Does that make sense to everyone so far? Okay, cool. So now we want to just update the number of evens and the number of odds we have. So how do we check if a number is even or odd? What can I write here?
Just use like a mod2 operator.
Yeah,
If
percent
mod2 is
sign.
equal to 0, then it's even. If mod2 is not equal to 0, then it's odd.
Yep, exactly. Okay. Cool. So now we have our number of evens and our number of odds. So now let's think about our actual algorithm, right? Our algorithm was basically like greedily transform odds into evens if there are more odds than evens. Right? And so we can just do this with a nice and easy while loop, right? So while the number of evens, or rather the number of odds, is greater than the number of evens, we can take the number of odds and subtract out 2, like we said, right? Because 2 odds make an even. And we can increment the number of evens. And so this does our greedy step of transforming. So now we need to do the check where we said, make sure num odds is equal to num evens, or num evens is equal to num odds plus 1.
Oh, wait, 1 sec. Why is num O equal to 2 now?
Why is it equal to 2 now?
Like you made num
Where is
O.
it? Oh, sorry. So this operation isn't an equal sign. It's a minus equals.
Okay.
So this is equivalent to num O is equal to num O minus 2. So these
I know,
statements are equivalent.
Why two? Because we in your stack, like in the whiteboard, you said when you take out 2 odds, it's 1 even.
Right, exactly.
Okay. Yeah.
Right, so we're taking out 2 odds, right? We're subtracting out 2 odds, and we're making 1 even.
And then you're doing this until your odd stack is greater, or like.
No, so how does this while loop condition work? This while loop is saying what does this convert this line of code into English?
No, it's basically saying like until num e is like when the condition is not satisfied, it'll stop. Like,
Right.
yeah,
And so in English, what is that condition?
this is basically it'll keep going when num 0 is greater than num e. I mean num O is greater than num e.
Right, exactly. So while we have more odds than evens, we're gonna transform the odds into evens.
Yeah.
Right. So now the last thing to do is we just need to make sure that either of these conditions hold, right? Because that's what we said must necessarily be true in order for this in order for the grouping to work. Because we start with an even, right? So we can either do even, odd, or we can do even, odd, even, right? So all we need to do here is we just need to check if num e is greater than num odd plus 1. We just want num e to equal num odd plus 1. And now we should just be able to print out num e plus num odd. Right, so let's see what happens on the first sample. We get 3, and then on the second sample, we get 5. And so we can submit this. Oh, I wasn't on whiteboard. I can share again. Oops. B, submit, okay. Cool. Are there any questions about the submission? I'm pretty sure this is going to work.
Yeah, once this is done, could you actually go back to the submission? I just want to review
Yes.
like the
Yes.
loops and the overall algorithm.
Yeah.
A little confusing.
Okay, yeah. So let's actually, I'd say let's actually ignore the code. So as you see, the code is very, very simple. And you can implement this in any way you want. Let's actually go back to the algorithm, right? I think the idea here is the tricky part, not the code.
Yeah, I'd agree.
Okay, so let's remember our objective here. Our objective is we want to group these numbers, but we want to do like as little grouping as possible because we want as many groups as possible, right? And so the first thing I think kind of to think of here is what are the total number of groups, or the relation between the number of even groups and the number of odd groups that we'll have, right? And so that's where we got this right side of the board, right? Does this make sense, the right side? I think this is a good starting point. Does it make sense?
Makes sense?
Okay. So now the question just becomes, how do we actually like make these equalities hold true? And there's kind of two cases here, right? And so I'll leave these images drawn up of our stacks. The first case, and I'll use this one first because I think it's the simpler one. The first case is if the number of evens is greater than the number of odds, right? So if we're in this case, then we know automatically our answer should be this, right? The question just becomes like how many, right?
Wait, this is evens equals odds plus 1, right?
Yeah, so if we have more evens than odds, then we literally just set evens to equal odds plus 1, and then that's our answer, right? So it's evens plus odds is going to be our final answer, where in this case, evens is defined as odds plus 1. So you can actually just do 2O plus 1, and that's your answer in this case. in the case where we have more evens than odds. Does that make sense? Basically, like you can think about it like evens are our free currency. Odds are the ones that we're dependent on. Because we start with an E, but the only way we can proceed in our conditions is with an odd, right? So if we're in the scenario where we have more E's than O's, right? The O is the limiting factor here. And there's no way to transform O's into, there's no way to transform E's into O's.
Wait,
Does that
why?
make sense? Oh yeah,
Oh,
sorry.
like 2 O's can be an E, but it's not like 2 E's can be an O.
Exactly.
I think so. So is that why you can't, or is that why we don't ever want to have more odd groups than even groups like OEO, because odds are harder to make? So they're
So the reason why we don't want OEO is because this is actually illegal according to the problem. If we look at the problem statement, or yeah, if you can just check the problem statement on your own computer, right? Read what it says. It says specifically, it says, Farmer John has a particular idea, whatever, and then line up the groups so that the sum of the breed IDs of the cows in the first group is even. That's the key line.
Oh, my bad. Okay.
Right? So the first group has to be even. And so that's why I drew out these examples. We only have these two cases. They always have to start with even, but it can end in either O or E.
I have a question.
Yeah.
So, like we took the case of like if the evens, if basically in the red pen, if the even stack is bigger than the odd stack, but like I'm still a bit confused. Where in the code did we do the odd stack is greater than the even stack?
Yeah. So we'll get to that in a second. Let's first finish talking about the algorithm, and then we'll go back and see where it translates in the code.
Okay.
Okay, so are we all clear on this much easier case of when E is greater than O? Okay,
Yes.
I'll take that as yes. Cool. So now let's consider the harder case, and I'm just going to erase this for now, just to declutter the board. Let's consider the harder case where we actually have more odds than E's. So let's think about what that means if in our progression of like stacking these people up next to each other. So if we have more odds than E's, then we can start with an E. And then we can obviously place the O because we have more odds, right? And then now here comes the question of like, okay, but do I have E's, right? Do I have E's to progress? If I have no more E's, then I can't progress, right? So here though, our hands aren't tied, right? Previously our hands were tied because there was no way to translate our excess material into the material we were lacking. But when we have more odds than evens, we can actually transform odd numbers into even numbers. So if we have a surplus of odd numbers, then we can actually let ourselves keep going by creating even numbers, right? And so the way we can do that is we take two odd numbers and we combine them, right? Essentially getting rid of them from the odd stack and adding one even number to the even stack, right? And so basically we want to keep on doing this until we have like the same number of evens and odds, give or take one, right?
Okay. Yeah.
And the give or take one comes from the fact that actually we can always have more evens than odds, right? Like we can have exactly +1 more. Okay, so and I urge you guys to think about this a bit more because also we're going to go over time on the third problem. I'm happy to stay. But yeah, so now thinking about this in the code, notice we don't have any if statements here talking about like if we're in the first case or the second case, if we're in the blue case or the red case, because we actually don't need it, right? What is this while loop saying? This while loop is only which case in our drawing? Which case is this while loop going to actually do logic on?
It was the second case where we have more odds.
Right, it's the blue case. This while loop is the blue case. So if we're in the red case, we're actually just going to skip this, right? So look at this code with this while loop not here. And this is the logic of the red case, right? Like we said, if we have an excess of even, we just set it to be num odd +1, and then we just sum them, and that's our answer, right? So this was the simple case.
Oh, so you use that algorithm there, like even if. you had the red case, you can do red and then blue, or you could just skip over it if it's blue from the start, right?
Exactly. And so we don't actually need any other if statements because, well, I mean, a while loop just is an if statement executed a bunch of times, right?
Yeah.
So like, is the code from line 16 to 20 for you, like the part where we're just making our stacks?
Correct. Yeah. The stacks, it was just a visual illustration of literally two numbers, the number of evens and the number of odds.
From 23 to 26, we're taking the condition of if the odd stack is greater than the e stack, and then from that you're just taking out 2 from the odd and putting 1 into the e.
Exactly. Because
And then
that's, yeah.
Yeah, okay. And then the 29 to 31, actually basically the 29 if statement is taking the other case of if the even stack is greater than the odd stack. Then yeah. I don't really understand the plus one. The plus one's like throwing me off.
Which plus one, like in this
Like both of
condition?
them.
Okay. Yeah. So the plus one is like, the plus one has to do with, the plus one has to do with this. Okay. So answer this question. So if I give you like an infinite amount of e's and I give you 5 O's, right? Or to make this easier to draw, let's say I give you 2 O's, right? But you have an infinite amount of e's. Which scenario is the optimal answer? The first one or the second one?
Second one.
The second one, right? So how many e's are there compared to the number of O's?
Plus 1.
Plus 1. So if I have a surplus of e's, then I know that I can do the number of O's plus 1 number of e's, right? And that's what this line is saying, right? In the second case, the number of e's is equal to the number of O's plus 1.
Yeah. Okay.
So that's what that logic's saying. Because if we have a surplus of e's, so if I have like 50 e's, then actually I need to set the number of 50 e's to be the number of O's plus 1.
Okay, so then there'd be like 49 O's in that case.
So in the case where we have like 50 e's and 2 O's, remember the O's are the limiting factor. So how many e's would there be if we had 2 O's?
There'd be 48.
Like how many e's would we use?
There'd be 3 e's.
Correct. Exactly. Yeah.
Okay. Yeah. And then so back to the code after the if statement, then you're just saying num e is the O stack plus
1. Sorry, what was the question after where?
In Eclipse, yeah. So then you're just saying the num e is equal to the O stack plus 1, and then you're printing. Okay.
Mm-hmm. Okay. Let's move on. If there's more questions, I can stay after and explain that as well. But let's talk about the third one. And maybe I should have started with this because I think this was the most difficult for a lot of students. But okay, does everyone, for the sake of time, does anyone need me to explain what the problem's asking, or does everyone kind of remember?
If you could really quickly skim through it.
Okay, so basically we have n cows and we have n barns. Each cow has a height and each barn has a height limit, which means that like if I'm 10 feet tall, I cannot go into a barn that has a barn that has a limit of 8 feet, right? Because I literally just can't fit. And the goal here is to count the number of ways that you can assign all of the cows to all of the barns. So more concretely, let me hop back to the whiteboard. Right, more concretely, if I have 4 barns of a certain height, and I have 4 cows, we'll call them 1, 2, 3, 4. Right, I can place these cows, and let's just assume all the cows can go into all the barns, just for the sake of the example. Right, this is one way I can organize the cows. What's another way I can organize the cows? I can put them like this, right? Or I can put them like this, so on and so forth, right? For a total of 4 factorial ways that I can organize or organize the cows. Is everyone familiar with this factorial, what this means?
Yeah, you just multiply that number by like the next number. Yeah.
Right, all the way down to 1, yeah. Okay, so they're asking us, what is the total number of ways that the total number of permutations that are valid? Where valid being each cow can only go into a bar if they're shorter than the bar limit. Oh, I keep on saying bar, I mean barn. But yeah. So does that make sense what the problem's asking?
Yeah, I think so. I
Okay.
didn't solve it, but like I got it later, and I feel so stupid because it was a short solution.
Yeah, I mean, I don't think I think this problem was challenging, you know, for bronze. I think like by short, do you mean like I don't think it was that short, like in terms of thinking, you know, like maybe it was short to code, but I mean,
Yeah, it was like a 20-30 line solution. That's it, and that's like with readability spaces and stuff. So
yeah, I mean, I think generally it's easy to get sucked into the way of thinking of like, oh, this is few lines, it's like an easy problem. That's often really not the case. You know, I mean, the last problem we saw was like I could have, if I condensed that's like a 4-line solution, but you know, it's quite a challenging problem. So don't measure a problem's difficulty by its lines of code. I think this was a pretty challenging one. So don't feel bad that you didn't get it.
Yeah, I have a quick question. So like the in the problem, yeah. So I read this thing where like there's like 4 ways that bronze is usually problems are categorized into, which is brute force, 2.0, and greedy, and math. Which one does this fall into? Because the previous 2 were 2.0 and greedy. Which,
What was the other one? This is I mean,
'cause
this one's also 2-pointer, I guess. This one's also 2-pointer and greedy. It's both.
okay,
Yeah.
because the other 2 I read, except those 2, were brute force and math.
Yeah. I mean, they don't have to give each problem category in each contest. But yeah, let's move on just for the sake of time as well to talk about the solution. So what are some initial thoughts here for this problem?
well, I just like when I solved it, I think the thing that I did was to try and deal with the most restrictive cases first. So using the tallest cow and seeing how many places it can go into.
Yeah, sure. So that's a thought that we can explore in a second. But I do want to point something out really quickly. It's always good to just consider a brute force solution and if that'll work or not. So what would like an idea for a brute force solution be here?
Try every permutation.
Yeah, try every permutation. So we can try every permutation and then we just check and see if the permutation works, right? And that's literally just we're just gonna straight up count the answer. So here we can talk really quickly about this idea of big O notation. Is everyone familiar with what this notation is and what it means?
Is it like a type of time complexity?
Yeah, so it's relating to time complexity. If people aren't familiar, I can explain it in more detail afterwards. But just for the people who do know, that algorithm we just discussed, the brute force, would be an n factorial n algorithm, right? And so when n is equal to 20, unfortunately, this number is really, really large and way too slow. And at the end, after we go over the solution, I'll talk about how to know when your solution is too slow or not. You can know this without even coding it. So if you notice in the problem statement, they actually gave a subtask where test cases 1 through 5 satisfy n is less than or equal to 8. So when you plug in n equals 8 to this formula, you get 8 factorial times 8, which is actually fast enough. So just this brute force idea, literally you have to do no thinking. You just have to implement it. You can get the first 5 cases, right? And I think if you get the first 2 problems and the first 5 cases, maybe that's enough to advance. I don't really know. But you can do the math if it's enough. But yeah, okay. So obviously this won't work for the full problem. So let's try to think about this. And we can use Advite's idea as kind of a starting point here. So kind of the motivation, right? It's like, okay, but how do you start thinking about, let's just look at the biggest cows. Well, and Advite kind of mentioned, the motivation for this is that the tallest cows have the least amount of barns that they can go into. And so it's like, okay, maybe like, since these have less choice, like we're kind of forced to put them in certain places. And so that's interesting. Okay, so we can be thinking about the tallest cows can only go into some barns. But what next? So let's actually push this further, right? I think often diving into the details is where you really iron out the solution. So let's once again stick with our four things. And let's say that I'm looking at the tallest cow. And the tallest cow, I don't know how to draw this. let's say that the tallest cow can go into like these two positions. Right? What's the next step? So we can keep in mind that like there's two positions that work. But hold on one second. Sorry about that. Okay, cool. So let's say that the biggest cow can go into two positions. Where can the next cow go? Where can the next tallest cow go? And it's kind of weird. This is very abstract, right? So whenever when I ask a question like this, and what you want to be thinking about in your head is oftentimes it's all about relationships, right? Because you can create an algorithm without actually like having the numbers themselves in mind, right? So you want to be thinking about like how these numbers relate to each other. So if I have my first cow, I'll call it C1, and it can go into these positions, then my next tallest cow, C2, I know can also go into these two positions. And maybe they can go into some other positions. But that's not necessarily true, right? But they can certainly go into the same positions as the red cows, as a red cow. Does that make sense? Yeah, okay. I'm gonna take that as a yes. Cool, so I guess now we can kind of think about like, okay, but how does this help us? How does this help us? So I have a certain number of positions that the red cow can go in, and I have a certain number of positions that the blue cow can go in. But how does this help me with like the number of ways I can assign my blue cow and my red cow?
Just multiply them.
Just multiply them. So in this case, you're saying we would multiply 2 by 3.
No, but you also have to subtract 1 because 1 is taken by the red cow. So 2 times 2.
Yeah, exactly. So if we think about this, so in normal ways that we do like combinations, permutations, or whatever, you can normally just multiply the number of options, right, for each cow, or like not for each cow, but like when you do combinations and permutations, like just for example, the idea of the factorial, right? How does the factorial? Why is the number of permutations equal to n factorial? This is the number of permutations.
How did you get like the 2 and 3 derived? That's kind of.
Yeah, this was just from my example here. There was 2 red arrows and 3 blue arrows.
And then those are cows, right?
Those are places where cows can go. Let me come back to this. I think this is actually a good thing to mention first.
Yeah.
So where does this formula actually come from? N factorial. Well, let's say we have like n slots here, right? And we want to think about the number of permutations, and we have a set of n numbers, right? So in this case, we could have 5 numbers. We can think about how we can place these numbers in positions. So how many valid numbers do I have to place in this position?
5.
5. And now I've used up my 5, or I've used up a number. We don't know which number I've used up, but I know I've used up a number. So how many numbers can I fit in this position now?
4.
4.
And 3.
And then 3, and then 2, and then 1.
Yeah.
And so this is literally where the definition of factorial, right? This is literally what it's related to. And now it's super obvious why the number of permutations is actually just n factorial, because I can literally place all of my people in one position, but now one of them is used up. So now I only have 4 for the next, so on and so forth. So we're going to use that same idea here. So C1 has 2 valid positions it can go to. C1 has 2 valid positions it can go to. And then how many valid positions does C2 have that it can go to?
Three.
It has 3 valid positions it can go to. But, and there's a big but here, it can't actually go into all 3 positions. Like it doesn't actually have that the decision to go into all 3 positions if we've already put C1 into one of these positions.
Okay.
And that's the same idea as this factorial, where I've used up a cow, right? So I've used up C1. So C1 is now sitting in one of these positions, either this position or this position. We don't know, it doesn't matter, but we know that one of them is used up. And since C2 will share some of the positions as the red one, we know that one of its options is also used up. So instead of multiplying by 3, we actually can only multiply by 2. Right? Does that make sense? Is this making sense? This is the key idea of the problem. So if this doesn't make sense, then let's talk about it.
So you're saying that you're multiplying the number of cows and subtracting. Are you always subtracting 1, or are you subtracting the number of cows minus 1?
What do you mean by the number of cows? Like n?
Yeah. Okay. So I'm saying, is the formula for this type of question, C1, like the number of. Okay, basically, is it C1 times C2 minus 1?
Well, so I guess I didn't actually define what C1 is, but I was just using that to represent the entity of the cow. But if C1 were to equal the number of positions where the first cow can go, then yes, in this case, it would be C1 times C2 minus 1.
Okay, I'm saying, like, okay, so if you take like the actual sample input they gave, and their cows are 1, 2, 3, 4, I think. Yeah, and spaced integers, the n cows.
Yeah.
So is it like 4 factorial minus 1?
Not quite. So why are you thinking it's 4 factorial minus 1?
Yeah, no, I don't think that's right. I don't know why I thought that. Is it like because so you were saying the way you should get it is you should take like the number of like which cow can go into which, except you're gonna subtract because you already took that cow. And since there's 4 different barn stalls, and there's 4 cows, then is it like 4?
But can each cow go into each barn? Right. That's the. So remember, these only represent the number of barns that each cow can go into.
Yeah. Okay.
Right.
We don't know that from the question.
Right. So we need to calculate these values.
Yeah.
But yeah, so that's the whole algorithm. So let's go ahead and actually implement it now. Yeah, I just want to make sure that we actually can get through the implementation, and then I can help more with whatever questions. Hopefully that generally makes sense. And I'm just going to go back to Scanner because it's simpler for the sake of time. Oh God, if I can type. Okay. All right, so what's the input? We have N, and then we have cows, right? And then we have, I'll just call it heights. Right, so now we'll just read in the first line, cows, oh God. And then we'll do the next line. And also, if you guys don't know, you can write things like this. If it's just a 1 line, you don't actually need the curly brackets. Okay, cool. So now the first thing was, what was the first thing in our algorithm? We wanted to consider these cows in descending order, right? We needed to do the tallest cow first. So we need to sort descending, which is equivalent to just sorting normally and going backwards, right? Which is what I'm going to do because I'm lazy. So we'll sort the cows, and now we'll just go through backwards. Okay, oops. Okay, so now we're going through backwards. And what was the first piece of information we needed to get for each cow? We needed to know how many valid barns it could fit in, right? So how many valid barns do I have? So how can we get this information?
Well, you loop through the list of heights, and you are keeping account of how many they work. So you need to declare that variable before the for loop. But then basically it's just a less than statement inside that.
Exactly. So we can have int num.
Wait, when you initialized your cow and height array, why are you using n for both of them?
Because there's n cows and there's n heights.
Okay, and it works, like it's not gonna throw the code off?
So sorry, what was that? Throw a what?
Like, and that works, but there won't be like, the code won't get confused because you're using n in both places? Question mark.
Oh, you mean like,
think
so you can use a variable as much as you want, right? Like we're not like redefining n anywhere.
I think it only gets confused if you have like nested for loops or something and using I for both like iterators. But other than that, I think this is fine.
Yeah, maybe I can answer afterwards, Pranav, as well. But yeah, okay. So let's get the number of valid barns. So if so like Ramsey was saying, so our current cow is cow sub I, and we're gonna see if they're taller, or sorry, let me do it the other way. If height of j is bigger than cow sub I. And so should this be bigger than or equal to, or does it matter? Does equality matter? We should always be careful about these things.
It's bigger.
I think it's bigger than or equal to. Well, are they allowed to match the height? Is that allowed?
You let me know. Read the problem. Let me know. I'll check too.
Okay.
Does anyone know? Does anyone remember or see it in the problem?
Yeah, they can match.
It can match. Okay, cool. So that means this should be equal to. All right, great. So now we have the number of barns. And so now we need to like utilize this information, right? So remember, the idea was that we would kind of do this factorial thing with each number, but we want to be taking the number of open slots we have, right, and then subtracting out the number of cows that have already been filled into these open slots to get our answers. So we can create our result again, and notice whenever you're doing multiplication, your initializing value needs to be 1, not 0, because otherwise the answer will just be 0. And so now we'll do our math, and to make it more clear for everyone, I'll do it like this. So what do we need to be multiplying by? And so notice like this multiplying by yourself is literally just like the way you do a running multiplication, right? That's the same way you would do running addition. So what should we be multiplying here? By here.
Num barns.
Yeah. So so that's close. So definitely num barns needs to be in there, right? But remember, num barns is actually an overestimate for how many cows we can for how many slots we have filled, right? Because remember, I might have 5 open barns, like I might have 5 valid barns, but if 4 cows came before me, then those 4 cows are already filled into some of those open barns.
Oh, right? I see. So it's
yeah.
Wait, so what like is num barns? Is that like our answer? Like the number? How is the number derived?
Yeah, so num barns is calculated here, right? So think about what this logic's doing, Pranav. And I think Ramsey, you were going to say something as well.
I'm trying to figure out how you could express it. Like if we have a certain number of barns like available and he's able to go in more, then well, if there are more barns available, then the answer is just num barns. But if there are not as many available, then it'd be like the difference between num barns and available. So I'm not sure how to express that in one line.
So num barns is the number of barns that are valid, right? That are valid height-wise, right? And what we need to do is we need to subtract out the number of cows that came before us because they've already been placed, right? So this.
Oh, I see.
Yeah.
Okay, and then like res is, yeah, and then what's res?
Res is going to be where we store the result.
So is it?
But if res is 1 and then you're multiplying it by 1, what's the point of res?
So what do you mean? I'm not multiplying by 1. Or like What do you mean? I'm not always
Oh, no,
multiplying
res
by 1.
numbers now. Yeah, res is equal to. Yeah. Okay. Never mind.
Yeah, Ramsey, did you have an idea?
Is it like n minus I maybe? It has to involve I, and I think since I starts at n minus 1, it should be n minus I or n minus I plus 1.
Yeah. So you're on the right track here, definitely. Yeah. So this is it's always annoying to like figure out this indexing stuff. What I normally do is I just like plug in an example in my mind. So it's like if I is equal to, like if I'm on the or I just like to substitute this in. So if you do n minus 1, right? So if I were to substitute this in, I is n minus 1, right? So n minus 1 is 1 for the first cow, but it should actually be 0 for the first cow.
Oh, okay. So
right. So it's
minus
close
1 on the end.
Yeah, exactly. And so I think we want to put these in parentheses. Right. And let's think about this. So this is n minus, yeah, okay. So I think this is right. Let's see. Let's run this.
Wait, no, but then doesn't it like switch the sign of I? It becomes like n plus minus n plus I plus 1. Or is that?
So yeah, if we do the substitution fully, and this is n minus 1, then think about how this distributes, right? So if we then distribute this is minus n plus 1.
Oh yeah, that makes sense.
Right, so then it cancels. Cool. So I believe what we have is looking good.
Wait, but like, can you really quickly revert back to the substitution you were showing? So if
yeah.
I equals n minus 1, right? So if
only on the first iteration, but yes, on the first iteration it equals n minus 1.
Okay, because I was gonna say then it's gonna cancel, so you can delete it, but you need it because it won't be just the first iteration.
Right, exactly. We want it to change, yeah.
Okay, thanks.
Cool. So yeah, so this passes the sample. Does anyone see any errors with this? Will this work, or might we have some bugs? Any ideas? Does it seem good? Let me submit. Or why did I say?
After you submit, I have a couple questions, but I'll just wait.
Yeah, definitely. Oh, sorry, I didn't see people were typing in the chat. Sorry if I ignored your idea at some point. It stopped giving me notifications. So this isn't gonna work, right? This isn't gonna work. And I think you guys can figure out why it won't work. Yikes,
Oh, yeah.
So we're getting some wrong answers. So
you're getting the wrong answer when the constraint is over, meaning when n is greater than 8.
When n
like
is
in
greater
6 to
than
12, it said
But
that
not a TLE though. It shouldn't affect like the answer though, right?
right. So if it was dependent on n, or I mean, it still can be dependent on n, but we're getting wrong answer. Are you talking about the time limit exceeded? Like our solution's too slow, Pranav? Or no?
I mean, the symbol isn't like it's slow, it's wrong, but
right.
coincidentally in air quotes, it's 6 to 12, which do satisfy no additional constraints.
Right.
So
but that doesn't mean that it's like it isn't too slow, right? Like we are getting wrong answer and it's not too slow. So I want you all to read the output format section really quickly. Is there anything different that they're saying here?
Oh wait, we have to use a long.
Yes.
For the integer.
Yeah. So if you see here, I made res an int. So does anyone know what the maximum value number res can hold is?
I think it's 2 to the 16.
No, it's 2 to the 31 minus 1, I think.
Yeah, exactly. So in normal numbers, that's like 2 times 1 billion, right? So 2 times 2 billion. It's a little over 2 billion. So let's think about it, and we're doing multiplication here, right? And we're doing a lot of multiplication. So that should probably give you some intuition that okay, maybe we're gonna overflow int, it's called, if our answer is a bigger number than int can store. So what is like the maximum kind of size in general that our answer can be? And so you're going to want to check the input format section to see they give all heights and limits are in the range 1 to a billion. right? So what are we doing? We're multiplying what?
Well, if like every stall works the first cal, you already have a billion there. And then if every other stall works the next cal, then you're already at 10 to the 18. So it's like pretty big.
Yeah, sorry. I actually messed up here. The size of the number doesn't actually matter. That's my bad. Yeah, it's relating to something else. So we're multiplying num barns here, right? So num barns is the value getting multiplied. So in the worst case, let's think about how big this can be. So like, what's like the largest num barns can ever be?
1 billion.
1 billion. So
and-
how does num barns become 1 billion?
If the tallest cow can go in every barn.
So if the tallest cow can go in every barn, that means, and num barns is 1 billion, that means that there's 1 billion barns, right? That's what you're saying?
Yeah.
Are there 1 billion barns? How many barns can there be?
The number of barns is
Oh, it's 20. Sorry, wait, my bad.
Yeah, no worries. I kind of misled you guys at the beginning by pointing out this. It's
the
actually,
number of barns is 20 because it's 20 cows.
yeah, exactly. They say that the number of barns and cows is the same, right?
Okay. Also, my code is giving me 0, like currently.
Yeah, okay. Let's take a look at that after. I just want to finish wrapping this up to make sure we can talk about this first. Yeah, so the maximum number of barns can be 20. And how many times do we multiply this? So we don't need to worry. In programming, we generally don't worry about like, oh, but it might be decreasing by like a small amount or this or that. Just like in the worst case, like how many times do we then multiply 20 essentially? Num barns can be 20 in the worst case. How many
Around
times?
20.
Yeah, exactly. So we multiplied 20 times, right? So 20 to the 20, right, is much bigger than 10 to the 9, right? Because I mean, you can just make this 10 and you just see it, right? So this means that we're definitely going to overflow int, and they tell us that the answer can in fact fit in the long. They'll guarantee it. So so we can just make this a long, and also it's good practice to, if your number's a long and you have a constant, to use this capital L after.
Does that screw up the number?
Yeah, so let's submit this and hope that this fixes it. Cool, and looks like it does. Cool, and there we go. One thing I did want to point out is, or talk about is, so we talked about the naive solution for this problem. We talked about the complexity. The naive complexity, which wouldn't work, was n factorial n. N factorial n. Now, what was the complexity of the solution that we just made together? And maybe if people are interested, I can just give a quick overview of complexity and how it works if you guys aren't familiar, because otherwise you probably won't be able to answer this question. Would that be good to do?
Wait, so you're asking what the time complexity of the code that we just wrote was?
Right.
Yeah, you can explain it. That would be better.
Yeah, okay, so I can quickly just go over big O notation. So
I think this, wait, just really quick. I think the sorting is n log n, right?
Yep, the sorting is n log n, but is that the slowest part of the code?
No, and then after that there's probably, I think, n to the n plus 1 log n, something like that.
N to the n plus 1 log n. Yeah, so this is massive, right? If you think about n to the n plus 1, this is bigger than n factorial.
Yeah.
Right, so that definitely can't be true given the fact that this would TLE, so that means this would TLE. But it's a good attempt. We'll figure it out. We'll figure it out in a sec. Let me just explain big O notation in general. And also feel free to leave at any time. I don't want to hold you guys here. You know, I don't know if your parents are making you do this or whatnot. But let's see what's in chat. Can you paste the input? Oh, what's TLE? Oh, good question. So TLE stands for time. See you, Jason. TLE stands for time limit exceeded. So basically, for each problem, your code is given only a few seconds to run to print out the answer. And so if it's too slow, it's time limit exceeded or TLE.
Okay.
Yeah, no
thanks.
problem, Daniel. Okay, so big O notation. So big O notation basically is a way that we analyze how long our programs take. So kind of the problem is motivated by, as you probably know, like there's slow computers and there's fast computers, right? And it's like, what makes a computer slow? What makes it fast? There's a lot of different factors that come into play, like hardware, also the language, like I talked about, this sort of thing. So in theoretical computer science, we want a way that we can analyze programs' efficiency without having it depend on the hardware, right? Or like actually to run it, because there's so many different machines. So this is where big O notation comes into play. And this is just a measure of how long a program will take as the size of the input grows. So your program reads in some input, right, described in the input section. And we're going to put this in terms of that input size, right? So big O notation will be in terms of that input size. And let me actually pull up code here. It'll probably be easiest to show. But yeah, so if we talk about the complexity of each section of code, we can talk about how long does this line take. So how long does writing this line take? This takes constant time, O of 1, it's called. O of 1 basically means like it's basically negligible. It's not like a repetitive event. It just happens in a singularity, right? So this takes like O of 1 time. Then there's something like a for loop, right? Does anyone have any guesses on how long this takes in terms of big O notation?
Like it depends what n is, right?
Exactly. So it's literally big O of n. So because it depends on n. So it's big O of n. This for loop is big O of n.
Okay.
Right. And so so you can kind of think about like, okay, I have a for loop, so that's big O of n. But what about if I have another for loop inside of here? That also goes to n.
Then it's like n to the power of j or something.
So j isn't really like j isn't like a real like j is like a variable we constructed, right? It's not really related to the input. So like how you want to be thinking about like the range of numbers j can be.
I think they both go up to n, so it'd be O of n squared.
Exactly. So this outermost loop takes O of n time. The innermost loop takes O of n time. So if you think about the total amount of time taken, for each iteration of the first loop, you take n time. And there's n total iterations of that loop, so it takes n squared time, right? You basically just multiply. So now this loop is O of n squared. Does that make sense to everyone?
Yes.
Okay. So now what if I do something like this? Well, what is the complexity here now?
N to the power of n over 2.
So be careful. So n to the power of n over 2.
No, that's wrong. N times n over 2. So that's like n squared over 2.
Right, exactly. So you would think that it's n squared over 2, but actually in our analysis, we don't care about constants, right? So in math class, you have coefficients and you have these constants, and like in your equations, that what you multiply them by matters. But in computer science, we're just like, actually, it doesn't matter. In the grand scheme of thing, dividing by 2, it'll barely make a difference when you think about orders of magnitude of difference, right? So this is basically saying that 1,000 is bigger than 100, but 200 is still much, much smaller than 1,000, right? So like we basically consider 100 and 200 to be the same, right? So that's kind of the idea. So we ignore constants. So even though there's an over 2 here, we don't write n squared over 2. It's still O of n squared. Cool. Now, what about a trickier one? What about something like this? So I've changed this condition to be I now.
Well, it's still O of n for like the I part, and then it changes how much j goes. So is it like n factorial? Does that make sense? Maybe I'm not sure.
Yeah, so it's a good thought, and I think a picture is worth a million words here. So basically, we had a for loop going to n, right, and then we had a for loop going to I. And so, like you said on the first iteration, so actually on the first iteration, when I is equal to 0, how long does this inner for loop take?
No time.
Right, no time. So I'll just like draw like a vertical line. Then on the next iteration, it goes up a bit. And then on the next iteration, it's 3. And then on the next iteration, it's 4. Right, and it keeps increasing by 1 every iteration until on the last iteration, it's n. Right, so this is like n deep. And this is n wide. So the normal for loop looks like this, right? Each level is a row. Right? The normal double for loop looks like this. Right? And we said how long did the normal double for loop take?
N squared.
Right, it took n squared. Notice it's the area of this, right?
Oh yeah. Well,
Yeah.
the top one kind of looks like half of the area.
It looks n squared over 2.
Exactly. So this is also n squared over 2, which is consequentially n squared. Right?
Wait, yes. How? Just, I don't understand.
What do you mean? How?
How do you just like suddenly multiply it by 2?
Oh, yeah. So you're not actually multiplying by 2, but remember what I said? We don't care about constants in our big O analysis.
Okay, so basically dividing by 2 is not that big of a deal. It's like it never happened.
Right, exactly.
Okay.
Because, and here's like a good illustration, right? So take 1,000, right? So 1,000 is 10 cubed. Right?
Yeah.
Take 1,000, and now take n squared. So n is equal to 1,000. N is equal to 1,000.
Okay.
What is n squared?
Like 1 million. So
Yeah,
can you
n squared is a million.
it's about 6.
Now tell me, does it really matter if instead of comparing like a million to like 10 cubed, does like or 1,000, like does it really matter if it's a million and 2,000?
I mean, they're both bigger.
They're both bigger, but like for all intents and purposes, like the 2,000 is minuscule compared to the million, right?
Yeah, so like basically the 2000 is less minuscule, but it's super small compared to million still.
In the eyes of the million, it's just as small as the 1,000,
Okay.
right? And so that's why we can ignore constants. Right.
Thank you, Samir. I think I have to go now, though. So
Okay, cool. Yep.
see you later. Bye.
Yep.
Yeah, I basically understood everything. I'm just having an output of 0, which is, I think, weird.
Okay, let me take a look. Can you share your screen?
So
Let me also stop recording here.
Okay.